Okay. Raymond Kui, 20. Raymond Kui, 20. Raymond Kui, 20. Adin Ghana, 15. Adin Ghana, 15. Adin Ghana, 15. Noor Mohammad Birbidikov, 17. Noor Mohammad Birbidikov, 17. Noor Mohammad Birbidikov, 17. Mohammad Syed Dema, 34. Mohammad Syed Dema, 34. Mohammad Syed Dema, 34. Masudu Zaman, 5.
Yes, Lashan here.
Okay. Ibrahim Rob Job, 20,
Yes.
29.
29,
Hello?
yes, sir. I'm
Okay.
here.
Okay. Mohammad Temakir, 30.
Yes, Lashan.
Okay. Mikhail M. Safa, 5.
Yes, Lashan, I'm here.
Okay. Solomon Carlton, 6. Solomon. Okay. Sador Dadajonov, 8.
I'm here.
Okay. Temur Marik Daminov, 10. Temur Marik Daminov, 10. Temur Marik Daminov, 10. Christ David Georgov, 12. Okay. Hasibu Rahman Noor, 14.
Yes, Lashan here.
Okay. Mehrab Hossein, 15. Mehrab Hossein, 15. Mehrab Hossein, 15. Janitor Fedas, 21. Janitor Fedas, 21. Janitor Fedas, 21. Abraham K. Kromas, 22. Abraham K. Kromas, 22. Abraham K. Kromas, 22. E. Sir Phillips G. Russell, 25. B. Sir Phillips G. Russell, 25. B. Sir Phillips G. Russell, 25. Solomon K. Sawyer, 26. Solomon K. Sawyer, 26.
I'm here, Lauji.
Okay, I see. Bethlehem Tirahan Mamo.
Yes, Lausha, I'm here.
Okay. Next, Laiken Asifa 30. Next, Laiken Asifa 30. Next, Laiken Asifa 30. Valery Butuk, 31. Valery Butuk, 31. Valery Butuk, 31. Anna Akulova, 32. Anna Akulova, 32. Anna Akulova, 32. Levan Takabo Gabramarin, 36.
I'm here.
So sorry, 33.
Yes.
Big Noir Ikram, 34. Big Noir Ikram, 34. Big Noir Ikram, 34. Big Noir Ikram, 34. Azamat Karimulin, 36. Azamat Karimulin, 36. Azamat Karimulin, 36. Okay. Okay. Let's firstly have a review about our last lecture. Okay, in last lecture, we mainly discussed the ARM company, okay, its business model, and the features of the ARM MPU, okay, or we say the ARM processor. So ARM, okay, ARM company, okay, was founded in UK in 1990. The ARM, okay, ARM, these three characters, okay, it stands for Advanced RISC Machine. Okay. ARM, its business model, okay, is the chipless production model, which means that ARM does not produce any chip by itself, or it also ARM does not design an entire chip. It just designs IP cores. Okay. So what is IP core? Okay. This is the IP core. Okay. And the rest part, okay, sorry. The rest part is the interface module on the chip. Of course, the IP core is the core part of a processor. Okay. Especially, it charges for the functionalities, including the instruction fetching, instruction decoding, and instruction execution. Also, okay, in the IP core, okay, it includes the MMU, okay, memory management unit, cache, bus, buffer, and many other hardware devices. Once the ARM, okay, finish its design of the IP core, okay, its partner will buy the design of the IP core and add their own interface on the chip so as to construct the entire chip. So, okay, the ARM's revenue mainly comes from two aspects. The first one is the license fee, okay, of the IP core, which means that its partner, okay, who purchased the ARM's design of the IP core, okay, will first pay a one-time licensing fee when they obtain the authorization from the ARM company. So this is the one-time licensing fee, which corresponding to the design of the IP core. Then, with the design of the IP core, the IC company will design and produce their own chip. Okay? So it means that they will design the interface module on the chip and produce the entire chip. So during the manufacture, it's okay. But once this chip has been sold, okay, then for each chip that has been sold, this IC company will have to pay a portion of the patent fee to the ARM company. So that this kind of chip sells more, then the ARM can get more money from it. So this is the two main revenue sources. Oh, sorry. it seems that I did not share my screen, right? Well, as fine that it is still on the course review, okay? Wait a second, let me share my screen. Abraham Kromas, you just came, okay? Let's see. Wait a second, let me share my screen. Abraham Kromas, 22. Okay, next time, please be on time, okay, Abraham? Okay, can you see my screen? Can you see the slides? Hello?
Yes, yes.
Okay. Okay, then we talk about the features of the ARM processor. Okay. As we mentioned before, the ARM mainly produces the MPU, microprocessor unit, which evolved from the CPU. So the ARM processor, or we say the ARM MPU, it is of the architecture RISC. So it has relatively limited instruction set, and its instructions has a fixed length. The processor of ARM usually is small and with low power consumption, low cost, but have comparably high performance. Generally speaking, ARM processor supports two instruction set: the sum, the 16-bit instruction set, and the ARM 32-bit instruction set. Also, it has a downside compatibility, which means that ARM processor can be compatible with the 8-bit and the 16-bit devices. Especially the 8-bit devices, it stands for a lot of the MCU. Okay? MCU, the single chip unit. Okay? A lot of them are still the 8-bit processor because of the price. Then, to maintain the high performance of the processor, although ARM use the RISC instruction set, okay, but it equipped with many registers to mitigate the problem that the RISC it is lack of many complex but powerful instructions, unlike the CISC architecture, okay, which have a lot of complex and powerful instructions. But you know that the CISC, okay, architecture will cause the processor to be relatively complex and need more power consumption and with relatively high cost. So with its many registers, okay, the ARM processor ensures the fast instruction execution speed. Also, many data operations are performed in the registers, and the addressing model is relatively flexible and simple. Today, when we discuss the development of ARM, okay, we will see something about some data operations and addressing model, okay, but not very in detail, just some simple ones. Okay, then there are some special techniques applied in the ARM processor, okay, to ensure that with the small size and the low power consumption, but the processor still can have high performance. So firstly, the data processing instruction can include both the arithmetic logic processing and the shift processing. and they optimized the loop processing, okay, that use address auto increment. Also, the load and store instruction can transfer data in batches, so that the speed of the data transmission can be increased. Then, when an instruction to be executed, okay, depends on the execution results of the previous instructions, so as to improve the execution efficiency of instructions. Okay, let's say today's new content. So last lecture, we discussed the ARM processor architecture. Now we will discuss the development in the ARM environment. Okay. Generally speaking, for ARM programming, okay, firstly, we need to understand the ARM architecture. Okay, so we already know something about it. Then we need to understand the C and assembly programming. So as I mentioned before, for the development in this course, okay, or we say for the development within the embedded system, since the application we need to develop are highly involved with the hardware, so that we need to use the assembly language to directly operate the hardware. Just speaking, operates the ports, registers on the hardware, and so on. Of course, this depends on the device drivers interface, which is provided to us. So anyway, C, because that it has the functionality called the inline assembly. Okay. So that C, to some extent, it can also operate on the hardware, so that we don't have to create the entire project using the assembly language. Okay. So here I mean that in this project, some source code, okay, are written in C. Some source code are written in the assembly language. Okay, so some source files are assembly files. Okay, and some source files are still C files. Okay, so let us say the mixed programming using C and assembly. Generally speaking, we will discuss these three things. Okay, firstly, the ATPCS, then the inline assembly in C. Finally, the function call in the C and assembly mixing program. Okay, that is okay. Next 30. Okay, let's see. Next. Okay, you are already late for. Okay, you are already late for 20 minutes. Okay, please be on time. Okay, next time. Next. Okay, what is ATPCS? These 5 characters, ATPCS, stands for ARM Some Procedure Call Standard. So ARM and Some, okay, are the 2 instruction set I just mentioned in the course review, right? The ARM is a 32-bit instruction set, while the Some is a 16-bit instruction set. Okay, procedure call. You know what is procedure call, right? Anybody can let me know what is procedure call? Anybody can answer this question? What is a procedure call? Anybody? Oh, let me pick up. Okay. Christ David Georg, are you here? Christ David Georg. Can you hear me?
Yes, Laoshi.
Yeah, can you tell me what is the procedure called? I think that when you learn the programming language class, okay, you should have learn something about it. Procedure call. Pardon?
I didn't get your
Okay.
question.
Sorry, can you speak loudly?
Didn't get your question.
Sorry, I cannot hear you clearly. So anyway, so the procedure.
Laoshi, I can try a little bit.
Okay, please, please.
I guess it is a sample of statement made by setting the procedure name.
Yes. Then.
Setting the procedure name is like, the term procedure call standard.
Yes, generally, yeah. Generally you are right. Okay, generally speaking, the procedure here, okay, stands for you can imagine that it's like the subroutine. You learn all the function, okay, all the methods, okay, in the C, in the basic, in the C++, or in the Java program, okay. So it's like that, okay. Generally speaking, okay, it is how we call the subroutines in the ARM sum program. So why we need to use this standard? Because that, okay, here we are using the C and assembly language mixed programming. So that in one project, it contains both the C source file and also the assembly ARM assembly source file. Therefore, in both types of files, they both exist many subroutines, so that it might be possible that in a C program, you need to call a function within which is implemented by the ARM assembly. Also, vice versa, in the assembly source code, it might need to call a subroutine, okay, implement in the C code. However, okay, you know that when you call a subroutine in the C, right? You know that you need to follow the prototype of that function, right? For instance, you write a function like the int, okay, sum, and the parameter is int a and int b, okay. Then the function body is return a plus b, okay. So this is a very simple C subroutine, right? Then we know that if we want to use this function, okay, we need to maybe in a C program, okay, we use d, okay, like a variable, okay, variable s, okay, s assigned with sum, okay. Then we pass two parameters, let's say maybe C and D to the subroutine, okay, and that is calculated by the sum subroutine and return an integer, okay, which is the summary of the A and the summary of the passing parameter C and D, then return to the main body of the program to the variable S, right? Okay, this is how we call the function in the C source file. But things are different, right? If we want to call this function in assembly language, okay, we need to have a different format. Similar case here, okay, if we write a function in the assembly code, how to call the function in the C program. Okay. Therefore, okay, we need to have in the this standard mentioned how can we make the functions call by each other. Okay, so we need to follow these three rules. Okay, register rules, data stack rules, and the parameter passing rules. Let's see them one by one. Okay, firstly, the register rules. The register rules, okay, in a normal ARM MPU, okay, it usually have 15 general registers, namely R0 to R14, and one program counter register. So, do you know what is usage of the program counter register? Do you know it? Yeah, so Lavan, can you answer me? Yeah, right. For looping, we indeed need to use that. Okay, but let's say exactly what is the value stored in the program counter register? So in other words, so what does the value stored in the PC, okay, point to? Points to what? Let me speak again, okay? So the value, okay, stored in the program counter, okay, PC, okay, register, okay. So what is pointed by this value, okay, or what is pointed by the program counter? Okay.
The instruction is to be executed, maybe?
The program counter, right? It actually stores an address, okay, which points to the next instruction to be executed in a processor. So that you answer that the looping, okay. When looping, you need to use the program counter. That's right. Okay. Actually, for the optimization, okay, I mentioned in the ARM, okay, technique, it uses address increment, okay, to optimize the looping. So it actually operates the PC, okay, by increment on the PC to optimize the looping. Okay, so let's say these registers. Firstly, R0 to R7. Okay. So this one can be used in all process models. Okay. So here, the so-called process models refers to the user model and the kernel model. Okay, you know, right? When you learn the operating system class, you know we have the different model, the kernel model and the user model. Okay, in the kernel model, okay, you can almost access to all the resources within the system. But if you are under the user model, you can access the limited resource within the system. Of course, okay, if the model is switched, okay, why the model need to switch? Okay, so we know that, okay, when a user application, okay, which is running under the user model, okay, invokes a system call, okay, then we know that if an application invokes a system call, okay, it will transfer control to the system kernel. So in this case, it will transform from the user model to the kernel model. Therefore, okay, when switching model, this value need to be stored. So that when the control is transferred back to the user application, this register can be restored. Then from the 8 to 12, these registers, each of them corresponding to 2 different physical registers, while the R14 to R13 and R14, they correspond to 6 registers. So which means that they can store larger numbers, or we say larger scale data. So here I need to mention that the R3 is usually used as a stack point, while the R14 in user model it is used as a link register. Stores the function return address. While in the exception handling model, R14 stores the exception return address. Then R15, which is a program counter register, it stores the value of the current instruction address plus n. So which means that we know that the program counter will point to the next instruction to be executed. So what is the n? So it depends on the length of the instruction. For instance, if the current instruction its length is 2 bytes, then here n is 2 bytes. But this is the case that the processor does not equip the pipeline execution functionality. If it has the instruction execution pipeline, for instance, the 5-stage pipeline, so which means that it can execute the 5 instructions together. So then the PC here, the n it will depends on it depends on the stage. Then data stack. So the stack, these data structures. Do you know what is a stack? Anybody can tell me what is a stack? Let me pick up one. Masudu Zaman, are you here? Can you hear me? Masudu Zaman, can you hear me? Hello? Masudu Zaman? Hello? Well. Ibrahim, Robert Job, are you here?
Yes, Lauscher.
Okay, Ibrahim. So, can you tell me what is the data structure stack?
Yes, we have in data structure we have the stack and flow. Queue. The stack is like the last thing you put on top will be the first thing that will be getting off.
Yeah.
So
right.
It will be at the start of the queue or at the start of like the last thing you put in will be the first thing to go out. So basically, it's unlike the queue. The queue is the first thing that comes is the first served, but for the stack is the opposite. Like the last thing that comes is the first served.
Yes. Right. Okay. The queue is the first thing first out, while the stack is the last thing first out. But this is stacks in most architectures. But actually there are 4 types of the data structure. with different incremental and the address generation. Okay. So here, the things you just mentioned, okay, the first in, last out, okay. So that means that the stack pointer, okay, will point to the last push data. So that anyway, if it is a stack, okay, then the stack pointer, okay, will point to the data that will be pop out, okay. So for these two kind of stack. Normally, okay, in most cases, we will use the second type, okay. So that the stack point, okay, it is called the full decremental stack, okay. That the stack pointer points to the last push data, okay, while the stack is generated from the high address to a low address. We can say that if it's an empty incremental stack, okay, then the stack pointer points to the next empty position to put the data, okay. So which means that it actually points to the place that after the last push data. Well, okay, if it's an increment stack, then the stack is still generated from a low address to a high address. On the contrary, if it's a decremental stack, okay, it is the stack is generated from the high address to low address. Okay. But in the ARM, okay, in the ARM language, in the ARM environment, the stack data structure is still the full decremental stack. Okay, so that the stack pointer point to the last push data. So the last in, first out. Then it's generated from the high address to a low address. Okay, so it means that the last push data, okay, is placed in the lowest memory address, while the first data pushed into a stack was placed in the highest address in the memory. Then the operation on the data stack is 8-byte aligned. So what is 8-byte aligned? Okay, so meaning that the basic unit of the data operation under the ATPCL standard is at least 8 byte, okay, or 16 byte, or 24 byte, or 32 byte, and so on. Okay. So anyway, so it is use 8 byte as the basic unit of the data operation. Okay. So if the data operation, okay, its size, its operands is less than the 8 byte, okay, then we will set 0, okay, to we will set 0 so that the operands length will grow to 8 bytes, and then we operate on it. Okay. Okay, then the parameter passing. So firstly, we know that function, okay, function always call a subroutine, okay, it can have no parameter, okay, then it can have several parameters, okay. Okay. So in a simple case, that this function, okay, have a fixed number of parameters, then the parameter passing is this. The first parameter will pass through the registers R0 to R3, while other parameters are passed through the data stack. So the pass through data stack means that the parameters are pushed into a stack and then pop out one by one. Then the next case is the variable number of parameters. Okay. Do you know any commonly used function that has the variable number of parameters? Anybody knows? Most functions, okay. For instance, most C functions have a fixed number of parameters, but there are still some of them have the number of parameters are not determined. Okay, so can you tell me any of them? Actually, there are some C functions that they are widely used in your code. Okay, actually, I think almost all your code need to use that function. Can you just think about it? Yeah. In Python, there are some other formats. Okay, but I say here I refer to C. Okay, because here we are discussing the C and the assembly. Okay, a mixing program. But here I refer to C. You have learned the C and C++ programming, right? C++ also okay. Okay. Actually, the grammar between C and C++, they are different, but not too much. Anybody?
Well, aren't the libraries from Python? Most of them are taken from C, right? So that's why I mentioned the modules in Python.
So wait again. So which program language so you have already learned? C++, the Python, and Java?
Yeah, Java and C++.
Java, C++, Python. Okay. I know. I see. Actually, okay, in C, okay, or C++, we need to output something, right? In C, then we will use printf-like functions. Well, in the C++, we will use things like the cout, right? But these two functions, their variables, the number of the variables actually are not fixed, right?
Yeah.
And I think that for every program you written in C or written in the C++ language, okay, you will need to use such output functions, okay, printf or the cout, right? Okay, so this is an example of the variable number of parameters. Okay. So in this case, suppose the number of parameters, okay, less or equal to 4. They are passed through the first 4 registers. While if the number of parameters are greater than 4, they need to be passed through the data stack. So, okay, generally speaking, okay, the parameter passing, okay, either go through the registers, okay, or go through the data stack. Okay, we just talked about the parameter passing. Okay. Then we know that most of the function or subroutine, they have a return value to be returned. Okay. So the return value, since the function, the return value is usually a single variable. So the parsing rules are not like the parameter parsing, not that complex. So they are returned using the registers. For instance, if the function return value is a 32-bit integer, then we will use the R0. Here, one register can store 32 bits. Then suppose this data's length is 64 bits. Okay, then we need to use 2 registers to store it. Of course, if the length of the return value data is even longer, for instance, it might be a float variable, or it might be a structured variable. Of course, generally speaking, we know that if when passing a structured variable, either it is a parameter or it is a return value of a function, we usually pass its address, not directly pass the entire struct, because the abstract variable may be very large, since the struct can have many fields, and each field can have substructs, so that to pass the entire struct is very time consuming and also takes a lot of memory space. So generally speaking, in that case, we just pass the address of the struct, while the address is generally 32-bit integer or 64-bit integer, depends on the platform. If it's a 32-bit platform, then the address is simply 32 bits. While if it's a 64-bit platform, then the address length is 64. Okay, let's say the inline assembly. So why we need the inline assembly? Because that most high-level language cannot directly handle the hardware. So that C has the inline assembly to handle this problem. Also, generally speaking, we know that the language is execution efficiency. The more complex the language is, the lower efficiency, right? So that the quickest execution speed of a language is machine language, right? Then assembly language, then the high-level language. Okay. So for the inline assembly, the ARM CC and ARM C++, here these two assembler support the ARM instruction set. Here is the 32-bit instruction set, while TCC, here T refers to the sum, and TCPP, supports the sum instruction set, the 16-bit instruction set. Okay. Although it is an inline assembly, but actually the instructions of the inline assembly in C includes most of the ARM or sum instructions, like the separate assembly code. But here we need to mention that although it is the inline assembly, okay, which is written in the same source file of the with the C code, but in the piece of the assembly function, inline assembly function, okay, you cannot directly reference the variable of C. Okay, you cannot directly reference any C variable. So definition. Okay. Also, okay, the data exchange also need to follow the ATPCS standard. In the piece of C code, okay, the inline assembly is usually implemented as a function body. And let's say this is a format. Okay, when it is start with the underscore 2 underscore. Okay, the prefix 2 underscore. Okay, then the following with a left bracket. Okay, and within the left bracket and the right bracket, yeah, the right one, right things. Okay, then within them, this is the assembly instructions. Okay. So for instance, here, okay, the MIS10 CPSR, okay, here is something like to copy the the register status, okay, to the variable temp. Okay. Here, temp is within this function. Okay. Then this is to clear, okay, the IRQ counter bit. While the MIS CPS are temp, okay, to load temp to the register status. Okay, this status register is a special register that refers to use 0 and 1 on each bit to indicate some certain status. Okay, so here just an example. You don't have to understand okay, exactly how this instruction works. Okay, this is because this is interrupt enable function. Okay, if you are interested, you can check how it works. But here is not the main focus of you just speaking. We don't have to do so hard coding. Okay, this is too hard for you. Here, let me mention again. Okay. So the prefix is the 2 underscore and ASM, then following with the brackets. Okay, within the brackets, we can write the inline assembly instructions. Okay, so here let's see some commonly used ARM instructions. Okay, so firstly, the move. Okay, there are several usage. Okay, for instance, move R0 to R1 and R1 is 2 operands. This means that we will copy the value okay, within the R register 1 to register 0. Okay, so here you can see this figure. Okay, before the value within the R0 is 23. Well, after the instruction is executed, okay, its value becomes 17, which is the same as the R1. Okay, here R1 is not changed. The value of R0 is changed. Then here, the compound, okay, the compound 64. Okay, this compound 64 means the immediate constant. Okay. So it's just the number, okay, integer number. Okay. So here, you just directly copy this immediate constant 64 to register R0. Okay, you can see that. Okay, after this execution, okay, the value of the register R0, okay, become okay. You know that this is the hexadecimal, okay? The hexadecimal 40, okay? The hexadecimal 40, okay, means is the 64, right? Of course, because this is okay. This is R0, okay, is its length is 64 bits. So that in this case, okay, the bits, sorry, is 32 bit, okay, while the 64, okay, just takes 2 bits of it. So that the 6 bits before are all zeroed. Okay. So you know that before, okay, these six bits have some value in it, okay. But here, although the 64 just okay takes last 2 bits, but the bits before them are all zeroed. Otherwise, okay, the value is not correct. This is similar here, okay. But the M and the move T, okay, move means that here T refers to a top. Okay, you can say that move to a top means that it just changes okay the first 4 bits of the register R0. Okay, please compare the two instructions. Okay, this is the move. This is move T. Okay, so move T means that okay on it rewrite the value within the R0 from the highest from the most significant bits. Okay, so that here you can see that the first 4 bits become 1, 2, 3, 4, while the rest 4 bits remains the same. Okay. Okay. Well, okay, the MVN, okay, so means that it copy, firstly, it copy the NOT, okay. You know the logical NOT, right? You know it, do you know the logical NOT? Yeah, so what is that? So let's say, suppose R1 is 1, 0, then what is the NOT of R1? No. If R1 is 1, 0, okay. Firstly,
did you say R1 1 0?
The one all the one, okay, all the one is become 0. All the 0 is become 1. Yeah.
I thought you asked it one.
So you can, you can see the example, right? Okay.
So didn't see.
So you can see the example. You can check. You can check it after class. Okay. Then the load and the store instruction in ARM. Okay. So the normal load, okay, LDR, just load 32 bits. Well, the load H means load half word. We know that 1 word is 32 bits, right? So that load half word, okay, means load 16 bits. Okay. But here means the load unsigned, okay, 16 bits. While the load SH, okay, means the load signed half word. While load B, okay, means load byte. Okay, 1 byte is 8 bits. While load SB, okay, load signed byte. Of course, there involves some signed and unsigned. Okay, actually, how it is used? Okay, it is corresponding to the signed type. Okay, unsigned type. Okay. Also, a store. Okay. Similarly, okay, a store. Okay, this str. Okay, stores 1 word. Okay, 32 bits. Then the store H again stores 1.5 word. While the store 8 bit, 8 byte, this is store 1 byte. Okay. But here, please be aware about that. Is here for instance, the store half word, right? It stores the rightmost, okay, means that it starts from the least significant bits, then the six bits of the registers. Also here, the rightmost 8 bits of register. Then let's say something about the addressing. Firstly, the immediate addressing. Okay. Here, the so-called immediate addressing is that here, for instance, 100, right? Okay, 100 is that compound 100. Then this is the this is simply immediate constant, right? Then here we move it, okay. Then R0 becomes the value of R0 become 100. Okay, so this is very simple. Okay, we don't have the data is already contained within this instruction, so we don't have to care too much about it. Then the register indexing addressing. Okay, this is widely used. Okay, so in this case, we have operands that is a register that contains the memory address of the data. So in other words, you know the pointer, right? Actually, it's like the point. So in this case, okay, load R0, okay, then the address of then the reference R1, okay. So here, actually, we do the dereference of R1. That means that we firstly go into the R1 and okay, and read the value within it. So here we read the value. You said that this is 2, okay, 004, okay. Then this is address. Then we check our memory, okay. Then we check this memory. Okay, then we see, okay, at the address 2000004. Okay, there stores a value. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, then this one is then this one will be passed, okay, to the R0. Okay. So here PC refers to a program counter. Okay. Then this one, okay, the 6808. Okay, this is the machine code of this instruction. This is the machine code of this instruction LDR R0 reference R1. Okay. Also here, this is also okay. This is also the machine code of this instruction. But be aware about that. Okay, you see the immediate constant, okay, 100, which is hexadecimal 64, okay, already contained, okay, within the instruction. But here, okay, we see that there's no such intermediate constant within the instruction. So we can consider, okay, the address is equivalent to an index into the array of the memory bus. Okay, and you can say that we can use this as array index to get the value stored in here. So here let's see some example. Okay. Let's say the load byte, right? Okay. One is here, okay. The load EX, okay. Then we say that this one is here, okay. Then assume R0, okay, is 2000, then it stores R1, okay. Sorry, E1, okay. Then also then the R1, okay. Because this is just load one byte, right? Now this is 1 byte, okay? You see, this one, this is the memory address, okay? Then this memory address is in the unit of byte. Okay, so in this byte, okay, it stores 8 bits. Okay, the E1. Okay, we know that in the hexadecimal, okay, this E, okay, and 1 refer is of 4 bits. Each of them is 4 bits, right? Okay, E is 1101, right? While this 1 is 0001, right? Okay, each of them is 1 byte. Okay, so here if we execute the LRDB, okay, load a byte, then the value of R1, okay, is simply at the rightmost, it is E1. While okay, if we load half word, okay, half word is 2 byte, then okay, it starts from here, okay, and E3, okay, the E3 and the E1. If we load a word, okay, then all the 4 bytes are loaded into the register 1. Okay, so you can see that. So this is a more clear example, okay, about the load edge. Okay, you can take a look after class. Okay, load edge is what and how it works. Okay, high the edge means highest, right? Okay, so that before load is 1, 2, 3, 4, 5. Okay, but after load, okay, wow. Then let's say, okay, some assembly languages support addressing called direct addressing, okay, which means that the operand address contained directly within the instructions. Okay. For instance, in our personal computer, okay, which is mostly the x86 architecture, okay, we can directly use things like that. Okay, move X Bob. While okay, the address of Bob contained here in this instruction, while the Bob is defined in a data area is 1526. Okay, then it can directly addressing in this instruction. But ARM do not support such direct addressing. Okay, because the 32-bit address cannot be embedded in a 32-bit instruction. Okay. You may still not understand why, right? Can you just think about this one? Why we said a 32-bit address cannot be embedded in a 32-bit instruction? Why? No? We know that the instruction, okay, is essentially some machine code, right? It consists of the command, like the load, move, add, sub, these things, right? Also includes the operands, right? Okay. But in the ARM, the instruction length is fixed and just 32 bits or 16 bits. Then here the address, address is one operand, right? But your operand is already 62 bits. Then, but the length of the instruction in ARM is fixed. Remember, this is RISC, and its length of the instruction are fixed. So that if you use a 32-bit address here, there's no command to be applied, right? And all the 32 bits are used by the address. Okay, so of course we cannot do that. So this is the reason. Sounds interesting, right? Just because of some, you can say the architecture limitation. So in most cases, in ARM we still use the indirect addressing. We just talk about it. The address can be registered, okay, can be in a register, okay, like that. Okay. Also, the address can be computed as a base address plus an offset. Okay. So this first case is here, like that, load R4, okay, R3, okay. So here we say that the load assigned ARY, okay, is the base of this array, okay. Then R3 the K is the address of the variable K, okay. Then R4, okay, R4, then we get the value of the K, okay. Then here is actually is to read the certain you read a certain element within an array, right? Okay, actually its address is R2 plus R3 is actually. Okay. So generally speaking, in the ARM assembly language, we need to use the indirect addressing, or we just use the immediate addressing. Okay. And then, okay, let's say some arithmetic instruction. Okay, so here we just use the add as the example. Okay, the sub is the similar. Okay, so the add. Okay, then in this case, okay, add R0, R1, and R2. Okay, then it's a computer process like that. Okay, so we firstly R1 and R2 are being processed by the adder, okay, in the processor. Actually, you know that actually the add, okay, is the basic instruction of all the arithmetic instructions, right? So actually, all other kind of the arithmetic instructions like sub, divide, multiply, okay, can be implemented by the add, right? Okay. So the add, okay, add R1 and R2, okay, and then okay, set the related flags. Finally, it stores the value, okay, to the register R0. Okay. Also, you can use the immediate operands. Okay. So here we use the immediate constant R2. Okay. So here it computes R1 plus 2 and stores it in R0. Also, okay, the ADDS, okay, ADDS. So here it will set the status condition flags, okay, based on the result. Also, okay, we can have some shortcut format, okay, like the two operand format. So it's like that. Okay, if we use add R1, R2, okay, then it actually equivalent to the add R1, R2. Okay, still the R1 will store the value of the summary of the R1 of sum of the R1 and R2. Also, okay, the operands, okay, is relatively flexible. Okay, you can have various types of the okay, so we can have a relatively complex operands in this instruction. Okay. So you can take a look at it. We do not discuss it in detail. I think that in the assembly language class, okay, you have learned it, right? But here we need to understand just use some of it, okay, not in too much details. Okay. Let's say the inline assembly, okay, its features. Okay. So the operands it can be registers, can be constants, or C experience, okay, like I just displayed, right? Okay. Then if we want to use a constant, okay, your constant as the immediate constant, then the compound you can here you can omit it, but generally speaking, it's still better to write it, okay, for better it can give you a better understanding of it, and also can provide a convenience to the maintenance guys. Okay. Here, the instruction B, okay, can use this is like the jump, okay, can use the label, okay, in the C, right in C code, but the BL cannot. Also, okay, the inline assembly do not support the pseudo operations, okay, in the general assembly language for memory allocation. So it still has some difference. Then, if an instruction contains constant operands, the instruction may be expanded into several instructions by the assembler during the compilation. Okay, continue to see the difference between the inline assembly and the ARM assembly, okay, the general ARM assembly. So the inline assembly cannot obtain the current instruction address by the dot indicator, okay, or it cannot obtain the current instruction address by the PC, okay, the program counter. While the inline assembly, okay, do not support, okay, the load, okay, something and the expression, okay, it uses the move instruction instead. Also, the label, label instruction not supported, and ADR and ADIL are not supported, and BX and BX are not supported, and cannot assign program counter. Also, okay, it uses 0x as a prefix of the hexadecimal values. Here you just know it as okay. We generally speaking, when we do the programming, we don't need to remove too much about it. Okay. Even you meet something, okay, you when you try to compile it, okay, the IDE will tell you, or the compiler will tell you, okay, you have this grammar error or the syntax error. Also, okay, there are some attentions for the inline assembly language. Firstly, when you use the assembly language, inline assembly language, please be careful about the physical registers, such as the register R0 to R3. It is because that when compute the C expressions of in the inline assembly in the inline assembly code, okay, the compiler may use these 4 registers to compute it, and also the flags like NZCV may be changed during the computation of the C expression. Okay. Then do not use registers to address variables. Okay. Otherwise, you may have some error reported by the compiler. While the compiler will save and restore the register it may use. Thus, users do not need to do so manually. Then, when you use the load and the LDM, okay, and the STM with registers, okay, only R0 to R3, okay, these physical registers are available. While the separators okay, in the comma. Okay, here you just know it. That's okay. You don't have to memorize it. Okay, let's see the function call. Okay, between the C language and the assembly language. So here is the ARM assembly. Okay, not the inline assembly. Okay, please be aware about that. Because of the inline assembly, okay, it is implemented as a function body of a C function. Okay. But here is different. Here is means that some function implemented, okay, in a separate ARM assembly file, source file. Okay. So generally speaking, there are three cases. Okay. Firstly, use a C global variable in assembly code. Then call an assembly function in a C code. Lastly, call a C function in assembly code. Let's see the first case. Okay. So access a C global variable. Okay. So we can access it indirectly through address. So to do so, we need to use a keyword first. Okay, the import. To import a C global variable. Then we can use the load or store, okay, instructions to access the variable through the address of this variable. Then for different type of variables, different load or store instructions are needed. Okay, so here you can see it. So for instance, okay, here the global underscore var, okay, it is a global variable, okay, defined in the main.c, okay, this source code, this is C source code, okay. Then here is the init.s, okay, s, okay, we do not, it is the postfix of the assembly, okay, source file, okay. Then if we want to use it, okay, we need to use the import keyword, okay, import global underscore var. Okay. Then how to use that? We need to firstly store, okay, the address of the global variable, okay, load it to the R5. Then we need to use the, okay, this register addressing key so that to access the global's value. Okay. So here, okay, then we add R4, 1, right? It's actually we store the value of R4 plus 1 to R4, right? So what is that? Okay, exactly, it is a global variable plus 1, right? Then we store the value of R4 to the reference R5. Okay, we know that the reference R5 is actually the address of the global variable, right? So here we actually write the R4 plus 1 is value, okay, to the variable global variable. So here, after the execution of this piece of code, the value of global where we are, okay, underscore we are, its value is incremented by 1. Then, okay, call assembly function in C. Okay. So to ensure the correct parameter passing, okay, we need to follow the ATPCS standard. Okay. Then the assembly function, okay, need to be called. It should be declared. Use the export, okay, pseudo function. Obviously, or you can also call the keywords as okay anyway. Then before invoking an assembly function, the function should be declared with the external keywords. Okay. So let's see. Okay. So here the INC, okay, external, okay, void INC, okay, this one, okay, this function, okay, is implemented in the init.s. Okay, we can say that this one is implemented use ARM assembly code. Yeah. So to use that, okay, we need to declare an external void INC. Okay, this function prototype in the C code. Also, okay, in the assembly language, okay, if we want to this INC, FUN, okay, this function to be used by the C function here, we need to use the procedure function export, obviously like the keyword export on the standard to mention that, to declare it. So in this case, after using the export procedure operation, then the INC function, it means that it can be viewed by the other side. Then to use that, it is use extend void INC function, because this function do not take any parameters. You see that, there's no parameters. It directly it directly operates on the global variable, on the global variable, global underscore VAR, right? So actually, this format, extend void INC FUN, this format is actually similar. Such format can also be applied to other C functions, which is not in this main.c, which is suppose, INC underscore FUN, this function is implemented, in another C file, also within this project. Then you can also use this extend, this keywords, to declare it. And of course, in other case, we usually need to we can use some header files to handle it elegantly. We don't have to, but if you check the source code like the Linux kernel, you can still view many of such things. So here, this one means like the jump. So it means here means that after this function is executed, it will jump back, to the main function. And finally, let's say last case, call C function in assembly. Still, we need to follow the ATPCS standard. But the difference that the C function does not need to declare itself. But in assembly code, it is necessary to declare the C function with the import procedure function. Generally speaking, the assembly code can use this DL to call a C function. It's like that. We directly jump to the entry of the C code. So here is an example. Let's see. So which function we are using? Actually, here we want to use the main. Don't be surprised. The main function is also a function. It can be called by a program outside. Don't be surprised about it. Although it is the main, we don't. It does not mean that everything starts with it. We can still invoke it. We don't. It does not mean that only when the program starts and we start from main. During the middle of the execution, from somewhere else, we can also jump to the main and start the execution. It is still a function. So here we say that it's import main. Then to do how to call it, because there is no memory passing issue, right? Because this is void, no return value, no parameter. So we simply use BL main, directly jump to it and to execute the main function. It's time. Today we finish here. See you next time. Bye bye.
Hello, Lao Shi.
Bye bye.
Hello, Lao Shi.
Hello.
Lao Shi, I missed the attendance.
Wait a second. Let me check.